Hello everyone, my name is Ruonan Ding, and this is Frank Wang. I am a full-time bootcamp student here. Prior to this bootcamp, I worked in insurance industry for the past 5 years, working as a pricing actuary, actually in the property and casualty field. That's part of the reason I was personally very interested in this topic and data set. The reason I joined the bootcamp was because I started using GLM, generalized linear model, in my daily work, and I realized there's a lot more room for me to improve personally and for the industry to start catch on. So that's why I started this bootcamp full time. Here I am.
Okay, my name is Frank Wang. My background is a PhD in physics. I spent more than 15 years in research library. Before coming here, I worked at the Stanford Linear Accuracy Center, part of Stanford, more than 10 years. Before that, I worked at the Brookhaven National Library, and before that, a lot of story. Okay. Anyway, I'm like a computation, like a number. So parallel computation is my daily work. So I guess that's my reason I come here, try to learn how to play with number, but a big number in another way. Thank you.
All right, so we'll start with the Liberty Mutual Fire Peril Loss Cost Prediction. This is actually the full name on the Kaggle website for this project. That was 2 years ago. So just a brief introduction on the product. Fire peril, fire insurance is one type of property insurance. So think about your personal house that you bought. So you buy property insurance on it. It actually covers fire, flood, or wind, or different perils. It depends on how much you pay your premium, what you choose your coverage. So for this particular case, we are interested in the fire insurance only. So here is the outline for today's presentation. Give you a little brief of what we're going to go through. So we'll start with the data set overview first. The goal for this competition is actually to predict the loss cost of total insured value of insurance policies, which means it's actually your claim amount over your total insured value. That's actually a ratio number. So the challenge for this data set is there are two. The first one is this is really a rare event. So you don't expect your house to catch on fire. So the chance of catching a fire is low. In this data set, over 450,000 record, we only have 1,188 record actually caught fire and filed a claim. So that's about 0.3% of the overall. And the other challenge is there are many features in this data set. We have total more than 300 plus features, and that includes both categorical, numeric, and with some missing values. Out of the 300 features, we can kind of divide them into 4 big blocks of data or features. So here is a brief overview of the raw features. As you can see, we have 17 policy characteristics, 9 in crime rate, 37 in geodemographic, and 236 variables in the weather variable category. So first step we decided to do is actually to do some feature engineering on that. Let's start with the crime rate, the yellow box first. So for crime rate and geodemographic, we actually worked with dimension reduction first using principal component analysis. So we were able to reduce the total number of variables down to 2 dimensions. And of the 2 dimensions, that actually explain more than 80% of the variance of different variables. And for the weather variable that is in the orange box, we actually started with the PCA first too, but it doesn't give us as much explanatory power as the other 2 categories. A dimension keep reducing very slowly as it goes. That's the other reason we looked at lasso L1 penalty method. And in the future, as Frank present, you can see how we actually play with the weather variables and see how that actually boosts our scores. But this is the final outcome of the tuning. We end up having 2 features remain using the L1 penalty method. And the most important is actually in the green box, the policy characteristic one. That is kind of the features you fill in when you buy a policy that you personally need to fill those information in. Out of that, there are actually a lot of missing values. So we deleted features that have more than 50% of missing values. That out of the 17 features were deleted. Those actually have more than 75% of missing values for those 7 features. And in that case, we were able to remain 9 original features, and there are category of features out of the 9, so we converted the categorical ones to dummy features, 1 zeros. So after the feature engineering in total, we were able to keep the 74 plus the 2 per box, that is 80 in total. So we reduced the feature numbers from 300 plus to 80 in this case. So this is kind of a overview, a snapshot of after feature engineering, how the data look like. Especially focus on the correlation matrix on the right. That the red is actually where you have correlation between the variables. But overall, this is a very clean data set. You don't see much correlation between the variables. So we look at this, we're like, okay, we can proceed for the next step. So here is kind of the outline of our thought process. We went through the raw data, we did the feature engineering in the second column. Now we're moving towards the scaling of the training data set and start our training step. So because this is a very rare event, we have only 1,000 plus record. And we want to run many models on it. Given the computational powers, we kept our sample fairly small. We kept 100,000 record, which includes all the 1,000 responses. And on that, we did different models and try to see the scores. You can see the model tried on that logistic regression, all that elastic net to GBM, GBR, gradient boosting regressor. And then the bold ones are actually has the highest score that we proceed with the full data set. So after picking the models, we train it on the full data set. And we use XGBoost as well. XGBoost was trained on the full data set too. Afterwards, we actually weighted average doing a blend of the 3 different models. So start with model 1.
This project mirrored the score in spatial called Gini Score. It's not popular, so I want to put this slide first to introduce what's Gini Score. For this plot, this is the number of samples, just like you show in the property, from 0 to 1. But the important is this that property is sorted in order. Have a low chance to claim insurance in that side, have a high chance to claim insurance in that side. So that's important. The sample, the property is sorted in the order of probability. The vertical just shows the total loss. From the company point of view, how many loss integrate? The normalized is 1 maximum. How I look at this score? Simple will assume every property have equal probability to claim insurance. That's not true, but simply we see that. Assume that way. That's the blue line. So that total loss is just the proportion of the number of property. So we call the equal probability line. What we done, use machine learning, we predict like XGBoost, predict the probability for this line. So what this means, for example, the total loss from insurance point of view, see from that side, the total loss grows slowly because we saw the possibility is lower for this kind of property. But if it go up quickly, they have a large possibility. That is the machine learning predict the high possibility in that side. So you can see it here, very steep. So that's why this area, this line correlated with the predicted possibility. The Gini Score, the definition is simple. The green area is area by the ratio A and plus B, that's 12. So large green area, a large Gini Score. What Gini Score measures just the possibility. Is equal possibility or no equal possibility. 0 is blue line equal, everywhere equal. If we have this line, the number 1, that's maximum 1. not equal, extremely not equal. So machine learning try to predict that kind of as much as possible to try to find which property really client insurance. Yeah, that's basically the most important. Well, familiar with this plot, positive, true positive, after that corner is corner. So some kind of correlation. It's just another definition. So we try to use the push machine learning, try to maximize this area, basically try to maximize the true positive data. This is the green line goes this way. Try to find who will claim insurance. So that plot gives you a possibility. This table shows the final result, the tuning, everything is good. It's good to show here, this plot shows how we step by step to improve our model. That's important to learn. As we said, this is at the first beginning, I have model A, because we have so many features. The company, there were a lot of features, but no name. We cut like from 300 to 100. We'll get a score like here. We decided the further away to cut the feature, especially the weather. We have 40. I don't know what's that. But we cut it to 2. We keep the 2 most important principal components, just the 2. Also, we drop some feature that have a lot of missing, more than 50%. And model B, we see the improvement. The prediction power actually increases when you clean the data, remove the missing data, remove a lot of data which is not related to the real event. That's model B. And further away, we just tuning the machine learning. For example, here, model C, we use a person regression instead of logistic regression. So different data maybe have CO2 different algorithm. In that case, in the real event, person regression works better than logistic regression. Anyway, always you need to try different things, different approach. The algorithm help, and finally, we use the whole data set to do red tuning, so that further improve your score. So we see step by step, we improve the score more than 40% by feature, by algorithm, by tuning the peril. So we learned a lot from here. This plot shows the feature that show, because the important feature is variable 15, 17, 30. I don't know what's that, but some number here, important. We do see some geometry and criminal and some weather. So that makes sense because that is fire, right? Depending on the location, could depend on the weather. So that's possible. Here we show another model. Linear regression with the elastic net. When we choose this approach because they have 2 tuning parameters. For machine learning, I like more tuning parameters to make your model more robust. Here this is the alpha, one tuning parameter. This shows the coefficient for more than 60 variables. I plot some of them in order to create. So we clearly see 2 variables important in this case. Some variable here. For this tuning, we're not using use this to select the feature. Instead, we use this to optimize the algorithm to maximum or score, which is the Gini score here. You can see the alpha of here. So see the alpha versus Gini score. So apparently, smaller alpha is good. So you can, that's why we're choosing 10 to minus 7 as our basic solution. So I have some detail to this way to tune your machine learning parameter to calculate a good score. Another point we want to see is that normally when log the response, get a better score. Log the response but in this case, it's not true. We want to log, but get a lower than score compared with don't do log for the response. So depend on case.
What is Gini?
So Gini Score is what explained on this plot. So we're going to go to the third model. This Gini Score is what actually used to measure your ranking for this competition on Kaggle. That's part of the reason that we have to use Gini if we want to be on the board. So this one is the gradient boosting regressor that we use for this data set. On the left is still the variable importance, which you can see for the top ones are actually pretty much in line with what the actually boost has for the importance. The order is different, a little different, but the overall ranking for the variables are pretty much in line. For the Gini score plot here, so again, Gini score is your area A divided by area A and B is in total. So you want your ideal curve is here you go, the chance of catching a fire is very low, but once you actually have a fire, your loss is going to go up. So you want a line looking like that, which is actually better in the case for the XG boost than what is have here on the gradient boosting regressor, because the line doesn't curve as much going to this corner as it does for the XG boost. That's part of the reason to explain the Gini score of 0.285 is lower than the XG boost one. And again, going back to Frank's point of taking the log on the response or not taking the log, not taking the log is actually giving us a higher score in this case. So again, the box here is after the fine-tuning. This is our final parameters. So I just want to show the result. Yep.
What is the meaning of this 0.285? I mean, what is that Gini score? Is it better for who? For insurance companies?
It is for insurance company. This is what the competition was evaluated on. So they actually rank you by, after submitting your result, it rank you by this Gini score. So it doesn't rank you by the AUC or any the loss, the MSE or things that we regularly use, but they use Gini score in this case, which is kind of the standard insurance industry practice, where especially for PNC, for property and casualty industry, all the events are very unlikely to happen in that case. It's high severity. If it happens, it's a big event, but you're not expecting it to happen that often. That's why you want the probability of that, the loss happening is low, but you keep it going for a very long time, so you actually don't have that loss for that long of time. Does it make sense? We can talk about it afterwards if you want.
You said there was a competition. Who was competing?
It's all the Kaggle competition per day.
Yeah. Okay, like moving forward. So this is our final result on that on the board. This you can see all the different models we tried on, and actually for the ranking for Kaggle, it's actually rate you on the private, which is a blind data set. You don't know the response. They will never release the response, the final result. So we were able, using the different models, especially the XGBoost, we were able to rank 23 overall on Kaggle. And I want to point out also XGBoost is the most robust model overall, because looking at the difference between the public number, the public and private, the drop is the lowest for XGBoost. Whereas for ElasticNet, your score is pretty good on the public, is 0.35 or 0.36, but then on the private, on the blind data set, you're actually getting a lower score. And for the final takeaways for this case, we want to stress that feature engineering is definitely a key. You can see how we step-by-step tuning that by decreasing and playing with the features. And also sampling technique is important for us so that we can try the most models we want on the shortest time we have. And the third one is Poisson distribution on the XGBoost increase the score a little bit, because Poisson is a good distribution. It's a discrete distribution, and it actually models the frequency of filing a claim in the industry. And the other thing is log transformation didn't really help in this case because pretty much everything we worked on is a tree-based regressor, which means we only care about the order, but not really so if you're taking the log, the order of these variables are still going to keep the same. Yep. Any questions and suggestions? Yep.
When you did PCA,
Right.
how did you arrive at the right number?
Right number of dimensions? Or?
Right.
So we look at so after you're doing the PCA, it will tell you by how much dimension, after the loadings, which loading give you what type of explanatory power, the variance. So it gives you how much by this dimension, let's say by second dimension, overall, how much variance can be explained by these two dimensions. So we chose 2 because for the 2 dimensions, we actually got more than 80% of overall variance of the features. Yep, I did use screenplot to figure it out. So that's the elbow point where it's above 1. Yep. Yep.
Can you talk a little bit about how you decided to use certain features? Like how did you go from 300 to that initial 40? And did you use a stepwise method at all?
Yeah. So I think first of all, for this data set, for competition purpose and just for the data privacy, Liberty Mutual doesn't release the meaning behind all the variables, but it does show for the crime rate, it will say crime variable 1. So that's how you know it's 4 blocks of data for weather. They will say weather variable 1. So that's first step. We actually split it into 4 blocks. So that's my initial guess that they're actually collecting 4 different databases for different things, and then they kind of merge it together for this competition. So that's how we separate them into 4. And then for the PCA reduction, that's what I kind of explained. That's actually the first thing that come into my mind because there could be correlation between variables that you don't know or you have to do a lot of tests to test on, but using dimension reduction, that kind of automatically release that.
But you have
74.
80 total, right?
Right. So 74 is really.
Did you start with all 80 in your model?
Yeah. So we start actually more than 80 with the model. This is our final result that we settle on. So the 74 is really because we make the dummy variables out of the categorical ones. So that is a lot. They have A, B, C, D to probably to Z. That's 26 after making dummies. Yeah.
Were you able to access any other data?
From my experience, I would say no. There is a chance you could access some of the data through the Department of Insurance based on the state that you live in. But most of the state require you to have a compliance department behind you and go in by person. Yeah. Any other questions? Yeah? Dimension is not the same as feature. Dimension is not. So that's why you use the dimension to kind of regenerate 2 new synthetic variables. It kind of give you, let's say, this first dimension have 30% of this variable, 20% of the other variable, and then you kind of use different distribution of different variables in that first dimension to create a new synthetic variable. Yeah.
Is that ongoing Kaggle competition?
No, this is 2 years ago. Yeah. Otherwise, I wouldn't know the score on that. Yeah. Any other questions?